All right, in this last segment of the intermolecular force chapter, we have to remember that there are more things in the world than molecules. Molecules are all the plants and animals. And much stronger than the plants and animals is the rocks and the dirt, and those are the non-molecular solids. So the easiest way to recognize the difference, especially for that matching section that you're going to see kind of towards the end of your homework, molecular solids, those are going to be all nonmetals. And when you're all nonmetals, you're sharing electrons. And when you're sharing electrons, maybe you're not sharing them so equally. So that's where the big differences of hydrogen bonding, dipole-dipole, and dispersion forces come into play. Is these guys over here are polar, and then these guys over here are what's left over in nonpolar. So it's still important to recognize that that's a majority of our last three chapters. But we still need to remember that if you're non-molecular, you're going to have a metal and then a nonmetal. In many cases, that's going to be a metal cation, a nonmetal anion that are hooked together. Those are the ionic bonding kinds of compounds. We also just have metals with no charge. Those are the metallic ones. And then we do see some covalent networks, and that's when we have actual covalent bonds that have to break, and those are things like diamond and graphite that are super strong. So we'll see examples of all of those coming up. So I already talked about molecular solids. That was most of the previous videos. What we're going to focus on is the leftovers, and those are things that are metallic. Metallic are going to be pretty strong because of their ability to conduct electricity. You can imagine that the aluminum wires, the copper wires that are hanging above the streets, those are allowing electrons to move through them. So in a sense, they're sharing electrons with the power plant. Their ability to share those electrons requires them to get those electrons back. So you can imagine if one gold atom wants to fall apart, the electrons from over here have to go back with gold at the right amount of energy and the right amount of time for that gold atom to kind of fall off and for it to melt. So these temperatures are very high, or can be much higher than, say, molecules that kind of top out around 100 or 200 or so. Doesn't mean there's exceptions outside of that, but they are much stronger than tissue, because you can take a knife made of iron and it cuts right through muscle tissue, and the only thing that's really going to stop that is bone, and bone is ionic, not covalent. As we look at ionic solids, these are going to be in that same relative category. So we have this kind of 300 to 1500 range. What's nice about ionic solids is they have recognizable suffixes that we've seen before. So this IDE, this ATE, this IT is very recognizable. Probably gives you full body shivers from exam 2 material. But they're easy to recognize because these are ones that would cross charges. And if you have real positive and negative charges, you're going to have real strength. And that's what we're looking for in this kind of chapter. Much stronger when you have a metal than when you don't. And then we have the strongest of the strong. Those are network solids. So here you're breaking bonds, not glue. That's the major difference. So if we were looking at, say, water has polar covalent bonds. It also has attractions to other water molecules. This attraction here, we said earlier, was hydrogen bonding. That's worth about 16 kilojoules. But these bonds here, these polar covalent bonds, those are worth like 400 kilojoules. So when we say network solids, we're saying break these bonds, so these bonds, not break the glue. So when we're breaking bonds, we're snapping those 400 kilojoule bonds. And that takes a tremendous amount of energy. So these are going to be in that kind of 3,000 plus degrees Celsius kind of range, because it takes a tremendous amount of energy to break shared electron bonds. It's pretty easy to break glue, but it's super difficult to break carbon-carbon bonds of, say, diamond. It's one of the strongest things on the planet, and that's why you're breaking the actual bond, not the intermolecular force, not the glue between them. So as we look to classify strength, we kind of need to get a recognition of, who's who. So here's a quick little cheat sheet. As you go from molecules, you really have three choices. You have nonpolar dispersion forces, you have polar dipoles, and then you have superpolar, which is your NHs and OHs and FHs. Again, to be polar, you have to be 0.5 or larger. Here you're going to be, less than 0.5. And all of these are going to be in that classification of molecular. And that'll get you to about, say 200-300 degrees. Beyond that, we really have two categories, and that's ionic and metallic. And then beyond that, and that'll get you to about 1500 degrees, you're going to have network solids like the diamond and like the graphite and quartz that are going to go to 3000 plus. So the major difference between these is very partial charges, super partial charges, real charges, actually no charge at all, so it's just a metal with no charge, but they do share electrons and their ability to conduct electricity. And then network solids is the actual non-metal to non-metal bond that has to break. So that's the reality of strength. Here we have partial charges. Eventually we get strength with real charges because we've lost and gained electrons, or we're just metallic and we're just heavy metals. And then we're actually breaking bonds. So that's the reality of when you look at an example, you're looking at this kind of context. So here's a few examples, and then this chapter's in the bank. So as we look at zirconium, we look at its temperature of almost 2000 degrees, and that gives us a clue of what kind of answer to provide. Zirconium is actually number 40 on the periodic table. And when you find number 40, you're going to see that it is a transition metal. So transition metals, definitely going to be metallic. And that's why we see that temperature getting pretty high. A little bit higher than we'd expect, around 1500 is what we said. But there again, there's plenty of exceptions. We look at lead. Lead is number 82. It's a main group metal. It's in group 14, beneath carbon eventually. And because it's a metal, it's also metallic. So notice this temperature is a lot lower, and that just means it's going to be easier to recycle. So a lot of times they want you to recover your car batteries and turn them back in for that core charge, and that's because this temperature is pretty low. You can melt lead pretty easy, make your own fishing sinkers and bullets and so forth from them. As we get to calcium nitride, we notice that it ends in IDE. It also has charges that were crossed. And the temperature was pretty high. This definitely tells us that we are ionic, because we came from that calcium +2 and nitride -3 ion. Graphite is just carbon. These are carbon-carbon bonds. Particularly, they are double bonds with single bonds in graphite that we saw back in organic chemistry. And notice the temperature is through the roof, well above 3000. Graphite was one of our three examples, along with diamond and quartz, as being a network solid. And then yellow phosphorus, the lowest temperature of all. Phosphorus to phosphorus, that's going to be 2.1 to 2.1. That's a zero difference. That's nonpolar. And if you're nonpolar, the best you can have is London forces. So you're going to be driving that tricycle. Definitely not the Ferrari of forces like hydrogen bonding, because there's no OHs or NHs. And because you're attached to yourself, there's no chance for a dipole. because you're sharing perfectly equal. So this is the kind of process you want to go through. Recognize suffixes, recognize nonmetals that are sharing in their electronegativities, recognize metals on the periodic table, and then recognize things like graphite, diamond, and quartz specifically as the 3 examples to look out for our network solids. And that finishes this chapter.